Hello and welcome to SG Tech Forum. I hope you guys are staying safe. Today we are going to discuss a core networking topic, right? When I say core networking topic, that means like our regular TCP/IP routing switching kind of thing, right? So we are going to talk about multipath TCP or MPTCP. Before I start telling you what is MPTCP, let's see why MPTCP. My assumption is you have watched or you already know what is TCP. And if you don't know what is TCP or you want to refresh your memory, then please feel free to watch other videos where I am talking about TCP extensively. So multipath TCP is an extension of regular TCP. Let's understand what is the need for this extension, right? What kind of problem it is solving or what kind of advantage it is bringing. So nowadays, all our endpoints, they are dual stack. When I say dual stack, don't mix it with IPv4 and IPv6 addresses. Dual stack means they are multi-home. That means they have more than one NIC card and probably more than one IP addresses. For example, your cell phone. Your cell phone has a cellular connection. Your cell phone, when you stay at home, you have a Wi-Fi connection, right? So at the same time, it has two IP addresses. Same story with laptops and other devices, right? Though you have more than one NIC card IP addresses, but at the same time, TCP is using one only. It is you're not able to take advantage of combination of those NIC cards, right? And that's where MPTCP comes into picture. Multipath TCP is a set of extension to regular TCP to provide a multipath TCP service which enable transport connection to operate across multiple paths simultaneously, right? So this is the promise of MPTCP, that if you have more than one IP address at the endpoint of your, if you have more than one NIC card, you can get advantage of combined power, right? But before we start discussing more about MPTCP, let's look at the little bit history. MPTCP is not a new protocol. It was first published as an informational RFC in 2013, and since then it is only lot of developments are there, and it's only moving ahead, right? So in 2013, RFC 6824, the MPTCP version was version 0, and now there is another RFC where we have upgraded the version to MPTCP version 1. And in my later video, I'm going to tell you very briefly about the difference between version 0 and version 1, what has changed from 0 to 1 and why, right? But that we will save for the last. For now, let's understand TCP, multipath TCP, right? Is there any practical use cases or practical implementation? If you're wondering, yes. So if you are on Apple Gear, like Apple iOS phones, you will see that Siri, the voice assistants, it actually uses, the stack is MPTCP enabled and it uses multipath TCP. So there is an actual implementation of it. Why Apple decided to do that? Because when you move from your Wi-Fi environment to cellular environment, it can keep the connection ready and there won't be any drop between the Siri transaction. Other operators worldwide, they have also experimented with MPTCP, and they try to combine the Wi-Fi and 4G and see how they can reach the greater bandwidth, right? So that is some practical implementations are there. All right, but there should be some guardrail, right? If you are bringing MPTCP into picture and then you have tons of legacy devices which are only TCP only, MPTCP should not get unfair advantage, because if that happen, you are violating the base principle of TCP, which is friendliness, right? So with MPTCP also, you have to guardrail or you have to qualify to that, those primary ideas, right? And what is the primary ideas? Improving throughput. MPTCP throughput is larger than the single path TCP by sending the data through multipath simultaneously. right? Because you are aggregating nicks. TCP friendliness. MPTCP does not incur any negative effect on conventional single path TCP. So it's not going to harm any TCP flow. So do no harm. That is the second principle. And third is balancing congestion and improving resiliency. So wherever it is possible, MPTCP is going to divert the flow from heavily congested path to lightly congested path, because you can do multiple things. You can measure the RTT and then dynamically switch the path, other things, and improving resiliency, of course, because you have more than one path, right? So these are the qualification, that do no harm, balancing, and improving throughput, but to a extent where if you have two connection, one is 100 Mbps, another is 1 Gbps, you should combine, you should not go 110, you can go maximum 1 Gbps, right? Okay, so this is the multipath TCP architecture. You can see our OSI stack. Within transport, we have the TCP, and here in TCP, we have TCP1, TCP2, TCP3. These are in MPTCP called subflows. They are regular TCP flows. And on top of that, we have multipath TCP, or a MPTCP path manager, which actually coordinate with different TCP subflows. And we will see what is the role of MPTCP path manager when we actually take a deep dive into the architecture. All right. I hope so far you are convinced that MPTCP is a way to go in future. What happened in MPTCP, right? So MPT, for to extend this regular TCP and introduce a top layer like MPTCP path manager. Obviously, how you extend a protocol? You extend a protocol using certain flags or enabling new options, right? So TCP options has been always very powerful, and MPTCP is again relying on TCP options, right? So we have now new options field, and along with new flags where we can, which we can use to aggregate multiple paths, uh, so that they work as a single connection, right? So you have different regular TCP connections, but then on top of that, you have this path manager, which is seeing all this subflow aggregated as one single connection from end host to end host, right? So very briefly, what is happening here, you can see in TCP typical three-way handshake, initial subflow. So first you are going to say SYN packet, but within SYN packet you have now new TCP option called MPTCP option, and within MPTCP option we have MP capable uh, flag on. Along with that, we are sending some keys, other flags. Then what you are going to get, if the other end or remote end is also MPTCP capable, it is going to reply with regular SYN ACK, but this time the host is also going to enable MP capable flag. So both way we have negotiated that both the host can support MPTCP. And finally, final acknowledgement. In the process, we have received some keys. These keys will be used later. So first you have regular subflow, and now since both hosts are MPTCP capable, and if they have more than one addresses, which has the route to other remote point, then they will start addressing those, they will start advertising those addresses in next TCP handshake. But here the options are going to be different. With SYN, we are going to say MP join, and it's saying sending that I have this another address, some flags, receiver tokens, and these receiver tokens are used from the initial subflow. So receiver knows that this new flow is part of this original connection. And this is how the same third three-way handshake happen, and a new connection will be set up. And in TCP, connections are identified by four tuples like IP address, five tuple basically, uh, source address, destination address, protocol, and source MAC, destination MAC, right? Source port, destination port. My bad, not MAC. Sorry, it was a like moment of like blank in my head. Okay, what is the TCP configuration options? Based on the kind of operating system you have installed, there are few configuration options available for MPTCP. First is signal. That means it is going to only advertise that yes, I have additional address. Subflow. This is initiating. If you have subflow, that means you are actively trying to initiate a new subflow using MP join. Backup, you can also just inform and mark this new address as backup. That means do not use this for and set up a new TCP connection until the primary fails. Okay. Then we have the full mesh. So full mesh, as it sounds, it create a full mesh of subflow between client and server endpoints. So if you have two endpoints here and two endpoints here at both end, they will have full mesh connection. Basically 4 connections, right? MPTCP congestion control. By default, TCP implementations have the cubic congestion control, which is good or a little conservative about AIMD. But then here we have multiple subflows, so there are some active work going on to tweak the congestion control and make it best suited for MPTCP. So I have listed it just for reference: LIA, linked congestion control, opportunity control, and balance LIA. All right. Important link. This is the Multipath TCP.org. This is the organization responsible for doing all sort of development work. So please, if you are interested in MPTCP, I highly recommend going and checking this link. All right. MPTCP version 0 versus version 1. Version 0 was published in 6824 RFC. Version 1 is now part of 8684. So we will come back to this difference at very last, just before the demo. And yes, I'm going to give you a demo with Apple iOS. All right. So the idea is, since most of the implementations are running on version 0, let's quickly go through RFC 6824. Yes, we are not going to read RFC 6824 in the call, but I have highlighted some key things which we are going to touch base together. Okay. MPTCP is a set of extension of regular TCP to provide multipath TCP service, which enable a transport connection to operate across multiple paths simultaneously. So this is the idea of MPTCP, right? Then I have already shown you the stack. So this is the regular stack. Now the new stack has MPTCP path manager and individual flows, which we call subflows, right? So that's the individual regular flows are called subflows. Subflows are treated purely TCP flows. That means the sequence number, acknowledgement number, all part of that. Additional things, we exchange some tokens for locally unique identifier for multipath connections. It is also called connection ID. These are exchanged as a TCP, MPTCP options. All right. So these are some terminology you need to be mindful of. The discovery and setup of additional subflow will be achieved through the path management method. And this is where the MPTCP configuration comes into picture. You can have set it as a backup, you can set it as a full mesh, and other things. All right. MPTCP add connection level sequence number to allow the reassembly of segment arriving on multiple subflow with different network delays. Right. So you have multiple paths from source to destination. They may have different delays, right? Different latency. So we have to treat the data received at the connection level, and that's where the path manager comes into picture, and it treats both the flow as one connection, right? And we will come to know more about that, how that tracking is happen. Yes, here you can see this picture is very clear. The host A has two address A1, A2. B has two addresses, B1, B2. Initial connection setup. First is regular TCP connection setup, first subflow with MP capable, and then based on configuration, additional subflows get set up and utilized. If it is a backup, so just a backup will not be utilized to transmit data. But if it is a full mesh or other, you can actively use other subflows. All right. Initiating a MPTCP connection, I have shown you this in picture. So in SYN, you send MP capable along with some key and flags, and then three-way handshake happens. Uh, okay. Associating a new subflow with existing MPTCP connections. So next time when you want to initiate a new subflow, how you will associate that new subflow to the original MPTCP connection, that's where the token or keys come into picture, right? That's the glue to tie to subflows. Uh, Again, informing the other host about another potential address. This depends solely on configuration. If it is signal, it will just inform about the new address endpoint, and the flag what is used is add address. Okay. At the same time, that if that address is removed, that means you walk out of your house and you lose the Wi-Fi address, then MPTCP can withdraw that address as well by using remove address flag. Okay, this is the key part. So far we have talked about control channel of MPTCP. Now let's talk about data transfer using MPTCP. For data transfer, there is a new concept which comes. MPTCP uses a 64-bit data sequence number DSN to number all data sent over MPTCP connections. Okay, each subflow has its own 32-bit sequence number, which is regular, and MPTCP option map the subflow sequence number to data sequence space. So basically, uh, original sequence number, which is 32-bit, so you may have multiple subflows, they are mapped to DSN, right? That's how the mapping happens, so that at receiver end, we know that what all packets I have received, what all segment I have received, doesn't matter on which subflow they have arrived, right? But again, you have if you have different delay on varied delay on different subflows, buffer bloat may happen. So there are certain challenges with MPTCP, and the research is actively happening, right? Or the thing with MPTCP, the principle of MPTCP is all subflow share the same receive buffer and advertise the same receive buffer. There are two level of acknowledgement in MPTCP: regular acknowledgement and connection level acknowledgement. So basically, if you have two subflows, they are not advertising that their individual uh, buffer, receive buffer, but they advertise, they get the buffer information from above layer, which is MPTCP, and advertise it to the other end. All right. So that's where this option data sequence signal comes. And I'm going to show you all these packets in action when we go to demo. All right. Another thing is requesting a change in path priority. So you can actually prioritize one path. That concept is also there, right? Whenever you have multiple paths, you don't want to leave it as a chance, right? Which path is better and which path is not better. You want a control. So if you know that there is certain path which is low latency, let's prioritize that, and you can signal that using that certain flags. Again, closing connection. Closing connection will be again two layer. Regular TCP or subflows, they will close their connection as normal TCP, but then there should be a data MPTCP level connection closing should happen. All right. I want to show you the packet structure very quickly, and this is the MPTCP option. So we have kind, what kind of option it is. It is MPTCP option. Then what is the length? Then we have subtype, version, and different flags. Okay, so subtype and different flags, they are the two key thing for all the negotiations for control channel. Subtype and what are the different subtype and flags, I'll show you later in the video. Okay, so let's talk about flags. You can see we have flags A to H. A is reserved to indicate checksum required. So if A flag is set, that means is a checksum required. B is extensibility flag, and through H remaining bits A lot of flags are not used, but C bit is now used because if you have a load balancer sitting in between, you can make your load balancer um, MPTCP aware using C flag. All right. There are other extension like crypto algorithm and security, which can be negotiated using flags. Okay. MP capable option is used only in the first subflow in order to identify the connection. All following subflow will use join option. Please highlight this. Remember this. I'll show you that in our demo. You will find the similar behavior. So only MP capable was is negotiated once. Following that, host knows that the remote host supports MP capable, and they send different options. So starting a subflow, closing a subflow, they all can be controlled by various configuration options. So I think we are good. Very quickly, we have summarized what is this, and again the same picture. Here it is combined in one. So you have the first level of handshake with MP capable, the initial subflow, and then additional subflow can be joined using MP join. All right. So let's go and talk about see these things in action, and then finally we will come back and quickly compare version 1 versus version 0. All right, so this is my iPhone capture, and that is why earlier I have published a video how to capture network traffic on your iPhone. So if you have not seen that, the link is in description. The TCP refresher link and iOS capture link, both the links are in description. Feel free to go and watch that video. So I have followed the similar method and captured my um, iOS network traffic, iPhone network traffic. I have two interfaces, as you can see, 192.168. This is my Wi-Fi NIC or wireless. And then I have 100.74, which is the public IP address, and that's my cellular connection. The destination is in question is 17.33.9.1, and it is nothing but Apple Siri services. All right. So as you can see, source to destination, I'm sending SYN packet, and let's dwell into SYN packet. Here you can see TCP options. TCP options, I have MPTCP as an option, and if I expand MPTCP options, you can see uh, this is saying I am multipath capable. My TCP version is 0, and then I have certain flags set. Like you remember flag A to H. So the flag A checksum required is not set, but HMAC and SHA is set, right? So some flags are set. Also, I'm sending my key and a token. All right. What happened in response to that? I am getting a response from Siri, and here Siri is also telling me that I'm multipath capable and I have similar options set. So negotiation and also the key. So the negotiation has happened, and then SYN ACK confirmation goes through. All right. Then what happened? Regular data transfer, and next my source, the cellular interface, it reach out to Siri and ask for a join connection, and it sets some flags. What the flag it said? It set the backup flag. That means it is saying that I want to join a connection, but do not use this connection because treat it as a backup, right? And then they are using the receiver token and sender's random token, which were initiated in earlier SYN or Wi-Fi TCP subflow. So this way MPTCP or Siri knows that, okay, this 100 dot something is again part of 192.168.1.123. Okay, so here the control connections channel is happening. All right, now let's look at some data traffic. Okay, for data, as we are transmitting some data, we are getting acknowledgement back, and the acknowledgement is tracked at two level, at the TCP subflow level, regular TCP level, and data sequence signal level, right? So we have MPTCP options set in my regular TCP, but this time when you expand this, you will see um, the subtype is data sequence signal, and it is set to 10. So this is my subtype DSS, and then I have certain field set, right? Is this a finishing connection? No. If it is a data connect, see 8 number and all those things. Data acknowledgement is present, yes, present, and then we have data sequence number and subflow sequence number. So that tracking or parity is going hand in hand with connection level versus subflow level, and this is how the data layer is tracked. Okay, so we have seen control, we have seen data plane, and that's how it goes. Finally, whenever its communication is completed, the fin uh, finish or happen at the subflow level at the same time at data level, right? Okay, I hope you got the idea. Now let's go back to version 0 versus version 1 comparison. Okay, two RFCs, highly recommend. If you are interested in MPTCP, don't skip, read through this RFCs, 6824, 8684. 8684 define version 1 of the protocol, while 6824 define version 0. Version number is specified in MP capable. You have seen that in demo. That's why I came back to this difference after giving you a demo, because you have seen the field. You know what is the subtype and what are the flags used, right? So here you can see the version field will be changed, but this is not a major change, right? What else we are getting? We have changed a few things. The format is similar to the original version, but there are several modifications. The first is version number is set to 1. Second, MP capable option sent in first SYN packet no longer contain connection keys. So here you can see host A want to send a packet in a SYN, but it is not sending the sender keys. Sender key are only followed in SYN ACK and ACK stage. Okay, because it gives you more space to carry other TCP option in initial SYN packet. Okay. Third modification is MP capable define new flag called CBIT. So a new flag, as you've seen, the C is now in use. And if you have a CDN kind of environment, and if you have a load balancer which is getting all the requests from the field and front ending it, and then passing it to different servers, that scenario is called CDN. And with using CBIT, you can make CDN aware that different subflows are part of one single connection. Okay, so that is the second. Then the another modification is in version 0 we have add address and remove address as advertised address, but there are no authentication and not sent reliably. But now with version 1 we have some level of authentication available. That truncated MAC goes with add address or remove address, so we know that this is a legitimate server or remote side which want to add new connection or remove new connection. There is no spoofing going on. Good enhancement, right? Again, Multipath TCP version 1 now uses SHA-256 and it has deprecated SHA-1. Multipath TCP now include MPTCP as a reset option to indicate why a subflow has been resetted by peer. So you can now get a reason also. So these are some differences. And now finally, let's talk about what are the challenges. So the challenges are with MPTCP is if you have a NAT or other firewall, other things available, they may not understand MPTCP or may not recognize MPTCP options. And if a middle box doesn't recognize a TCP option, what it does, it changes it to no operation. So that in that mean your MPTCP thing is broken. Then you have finally Cisco is making their product MPTCP aware, and I'm going to paste this link. You can watch the read through this. Some of the security products or Cisco products, router switches, they are MPTCP aware. I hope you like the video. So thank you very much for watching. And if you have any questions, please let me know.